You've probably heard the term black box after every major aviation accident. Investigators recover it, analysts study it, conclusions are drawn from it. But here is what almost no one stops to ask. What exactly does it record? How does it record it? And what happens to that data between the moment of impact and the moment an investigator plugs it into a computer thousands of miles away? More importantly, how does a device small enough to hold in two hands survive an impact force of 3,400 Gs, temperatures exceeding 1,000 degrees Celsius, and 6 months submerged at the bottom of the ocean? Those are not marketing claims. Those are the minimum legal requirements the device must meet before it is ever allowed onto a commercial aircraft. Today, I'm going to break down the real engineering behind the flight recorder, not the simplified version, but the actual design logic behind why it is built the way it is, how the data is structured, and where the system reaches its limits. When a serious aviation incident occurs, the flight recorders are the first physical evidence investigators want to secure. They contain the closest thing possible to a complete, objective account of what happened on that aircraft in the final hours of flight. Without them, determining the root cause of a crash can take years. With them, the investigation can narrow its focus to weeks. But that creates an enormous engineering problem. The device that documents the catastrophe must survive the catastrophe itself. The aircraft may be traveling at over 800 kilometers per hour when it strikes the ground. The fuel may ignite on impact, producing fire temperatures that exceed the melting point of most structural metals. The wreckage may be scattered across a mountain range or sunk to an ocean floor at depths no diver can reach. And through all of that, the recorder must arrive at the investigation facility with every data point intact. That requirement, survive everything, lose nothing, is what makes the flight recorder one of the most precisely engineered components on the entire aircraft. In terms of its survival specifications, nothing else on board is held to a comparable standard. Let's establish the numbers, because they are the foundation of every design decision in this system. The recorder must withstand an impact shock of 3,400 Gs for a duration of 6.5 milliseconds. A severe car crash at highway speed generates peak forces of roughly 20 to 50 Gs. The flight recorder must survive forces approximately 70 times greater than that, compressed into a fraction of a second. The fire resistance requirement is equally extreme. The recorder must survive 1,100 degrees Celsius for 30 minutes. Aluminum, the primary structural material of most commercial aircraft, melts at 660 degrees. Steel loses structural integrity well below 1,000 degrees. The recorder must remain functional at temperatures that would liquefy the airframe around it. It must also withstand 260 degrees Celsius for 10 continuous hours, simulating the slow burn that follows a major crash. The crush specification requires surviving a static load of 2.25 tons applied simultaneously from every axis. And the deep water requirement, full functionality at 6,000 meters in salt water for 30 days, while the locator beacon on its exterior transmits continuously, without any external power source. These are not theoretical worst cases. They are the documented conditions investigators have actually encountered when searching for recorders in past accidents. Here is the first thing most people get wrong. They assume the black box is a single device. It is not. Every commercial aircraft carries two completely separate flight recorders, each with a distinct function, and each independently capable of giving investigators a full picture of the accident. The first is the Flight Data Recorder, the FDR. Its job is to capture the physical state of the aircraft in continuous numerical form: altitude, airspeed, vertical acceleration, heading, pitch, roll, yaw, control surface deflections, engine thrust levels, fuel flow, flap positions, landing gear status, autopilot engagement, and dozens of additional parameters. On a modern wide-body jet, The FDR records over 1,000 discrete data parameters, with the most critical ones sampled multiple times per second. The second device is the cockpit voice recorder, the CVR. It captures all audio on the flight deck, crew communications between captain and first officer, radio transmissions, automated system alerts, and all ambient sound from the area microphone, engine noise, airflow changes, mechanical sounds, and any unusual acoustic events during the flight. Together, these two recorders give investigators both the objective physical data and the human context. The FDR tells you what the aircraft was doing. The CVR tells you what the crew was saying. Synchronized to the same timeline, they allow investigators to reconstruct the precise sequence of events from first anomaly to final impact. And neither of them is black. The international standard color is bright orange, chosen for maximum visibility against ocean water, snow, dark terrain, and fire-scorched wreckage. The term black box most likely originates from early recorders arriving at investigation labs, covered in soot after crash fires. The name followed the artifact. The physical architecture of both recorders is built around one priority: protect the memory module at all costs, regardless of what happens to everything else. The outermost layer is the structural shell, fabricated from grade 5 titanium alloy or high-strength stainless steel. This shell is designed to deform in a controlled way, absorbing and redistributing impact energy through plastic deformation rather than transmitting that force inward. Its geometry, wall thickness, and alloy grade are all selected to maximize the kinetic energy the structure can absorb before deformation reaches the interior components. Inside the shell is the thermal insulation layer, typically constructed from a dry silica aerogel composite, approximately 97% air by volume, and an exceptionally poor conductor of heat. When the exterior is exposed to 1,100 degrees, the insulation slows heat transfer into the interior, to the point where the memory modules stay below their operational threshold for the full 30-minute exposure. It does not prevent heat from entering. It delays it. That delay is precisely what the specification is built around. At the center is the Crash Survivable Memory Unit, the CSMU. This is where the flight data actually lives. In all modern recorders, the CSMU uses solid-state flash memory with no moving parts. No magnetic platters, no spinning disks, no optical components. The absence of moving parts eliminates an entire category of failure mode that becomes critical under 3,400 grams loads. The CSMU is the only component the investigation absolutely requires to be intact. The outer shell can be crushed. The insulation can be partially destroyed. As long as the CSMU retains its data, the investigation can proceed. The FDR does not capture a video feed of cockpit instruments. It records discrete numerical parameter frames, structured data packets where every monitored parameter is assigned a value at a specific timestamp. Altitude and airspeed may be sampled 8 times per second. Vertical acceleration 4 times per second. Less dynamic parameters like fuel quantity once every 4 seconds. Every value is timestamped to the millisecond and written sequentially to the CSMU. When investigators retrieve this data, they load it into specialized animation software that drives a 3-dimensional model of the specific aircraft involved. The result is a frame-by-frame reconstruction of the entire flight, every control input, every system state change, every parameter exceedance, rendered as a navigable simulation that can be stepped through second by second. The CVR records 4 simultaneous microphone channels: the captain's headset, the first officer's headset, the jump seat, and the area microphone mounted in the cockpit ceiling. The area microphone captures what the crew microphones miss: the acoustic signature of engine changes, mechanical events, and sounds that occur when the crew is not actively transmitting. All 4 channels record to a continuous 2-hour loop, constantly overriding the oldest audio with the newest. The FDR and CVR are synchronized to a common time reference from the aircraft's avionics. This allows investigators to identify the exact moment a warning tone sounded on the CVR, correlated with the parameter value that triggered it, and match both against the crew's verbal response. That three-way correlation is the analytical foundation of most accident investigations. The underwater locator beacon on each recorder activates automatically on water contact and transmits a 37.5 kHz acoustic pulse every second. This frequency propagates efficiently through seawater across several kilometers and remains distinct from ambient ocean noise. Search vessels deploy a towed hydrophone array to detect and triangulate the signal. The beacon operates for a minimum of 30 days on its internal lithium battery. The flight recorder system has been the direct catalyst for most major safety improvements in commercial aviation over the past 60 years. Crew resource management protocols emerged from CVR analysis of accidents, where miscommunication contributed to the outcome. Ground proximity warning systems were developed from FDR analysis of accidents, where aircraft flew into terrain under full crew control. Recorder placement in the tail section is itself data-driven. Statistical analysis established that the aft fuselage consistently experiences lower peak deceleration forces and typically separates from the primary destruction zone during a forward impact. The system has real limitations. The 2-hour CVR loop is the most discussed. In accidents where a slow-developing anomaly began more than 2 hours before the final event, that recording has already been overwritten. Extending the loop to 25 hours is technically trivial, with modern flash memory, but revising certification standards across multiple international jurisdictions simultaneously is a slow process. Power interruption before impact is another issue. The recorders draw power from the aircraft's electrical system. If that system fails before the final impact, due to structural failure or fire, the recorder may stop writing data seconds before the event it is meant to document. At high-speed velocities, even a few seconds of missing data can represent the most critical phase of the sequence. In the case of Air France Flight 447, which entered the Atlantic in 2009, the recorders were not located until nearly 2 years later at a depth of 3,900 meters. Despite more than 600 days in the ocean, both CSMUs were intact and the data was fully recovered. So when you hear that investigators have recovered the black box, here is precisely what that means. They have recovered 2 devices, a flight data recorder and a cockpit voice recorder, each sealed inside a multi-layer structure engineered to outlast the aircraft carrying it. Each holds either a continuous record of over 1,000 aircraft parameters sampled multiple times per second, or 2 hours of 4-channel synchronized audio. Both streams are timestamped to a common reference and overlaid with millisecond precision. The black box is not a simple recorder. It is a deliberately engineered data vault, built on the explicit assumption that the aircraft around it will be completely destroyed before the data is ever needed. Every material, every geometry, every specification threshold exists because a real accident demonstrated it was necessary. That is the engineering logic behind the flight recorder. Not a black box, not a mystery. A layered, redundant, methodically tested survival system for the only record that matters when everything else is gone.